we're a little bit ahead in the lectures, and we've started working on this idea of transform methods. In particular, these are called Laplace transform methods. And there's also things like Fourier transforms and other transforms. And the basic idea is to take a problem that's hard, transform it into an easier problem, solve it, and then transform everything back, okay? And at the end of the last lecture, I think people were coming up and saying, well, okay, we can compute Laplace transforms, but so what? Okay, so we haven't got to this part yet, but we're going to use these transform methods to solve differential equations. Okay, that's basically what we're doing. So whether it's a Laplace transform or a Fourier transform, they're all based around solving some kind of problem. Okay, simplifying and solving some kind of problem. Okay, so before we get to this good stuff where we're solving all these amazing modelling problems, we just need to understand how a transform works and how we can sort of go one way and back the other, so transforming, untransforming, that sort of stuff. So that's why we're sort of not solving these amazing problems yet. We just need to understand what's going on. So how's everyone going at home? Hope you're well. Yeah. So what have we done so far? Let me refresh your memory on a Friday afternoon. Okay. What you see in front of you is the general form of a Laplace transform. Okay? So you'll see it's got a couple of things. It is an integral transform. It's the same as same sort of format as these Fourier transforms that you might see. And it's got an exponential thing in it, and we're integrating over the half line. Now, we're not sure why the structure's like that, but actually today, maybe, we'll see why we actually have that structure. Okay, why is that exponential there? Well, we'll find out. Okay, so from a method point of view, what you do is you take your f, you multiply it in there, and then you compute the improper integral, and you spit out some function of s. Now, usually in this course, we reserve capital letters for the transform and lowercase letters for the original functions of t, okay? So, you know, if we talk about capital G of s, that's the Fourier transform, Laplace transform of little g of t. Okay, so it's just some notation that you have to get used to. All right, so that's it. In the previous lectures, we basically used the definition 7.1.1 to produce these transforms, okay? To calculate some special cases, some case studies. You can see that if you do it the long way, you use Math 1131 techniques, which is improper integrals. Okay? And then I showed you the inverse transform, but only at a very superficial level. Okay? So this notation is to denote the inverse transform, the inverse Laplace transform of 1 on s plus 3, let's say. Okay, and they're the opposite actions. So a transform does something, the inverse transform undoes that. Okay? All right, and probably the most important thing that we looked at in the first lecture on Laplace transforms was the idea of a transform table. Okay? Right? So let's have a look, see if I've got a table here. Yeah, here's an example of a table. Right? This is in the the lecture notes that I've given you. The one that you get in the final exam isn't quite as comprehensive as this, but it's still got everything you need. Okay? So down the left-hand column, you've got functions of t. Down the right-hand column, you've got the corresponding transform of that. So, you know, if I transform the constant function 1, I would go down here and say, okay, well, there's 1. I look over here, that's the transform. If it's something like t squared, I would say, okay, t to the power m, go over here, 2 factorial on s cubed. Okay, so when we're transforming, we're looking down the left-hand side of the table, and sometimes we need to modify things slightly to make them fit, but we end up with something in the right-hand part of on the right column of the table. Okay, when we're doing inverse transforms, we are going the opposite way. Okay, we're looking down this column, and so, you know, this column is here. Okay, so this curly L, curly bracket f of t and this are the same. Okay, sometimes you want to represent them as functions of s's, other times you just want to say, hey, it's the Laplace transform of this t function. Okay, so it is a bit of a skill using the table, especially when the functions that you're dealing with don't quite fit. Right? Sometimes you've got to make them fit. Okay, so you've got to divide or multiply or do something. Okay, now on Wednesday we looked at some of these things down the bottom, right? So basically, to get any of these things, you can just do the integral, plug them in, do the integral, and you're fine. Okay, a few combinations here, and then we got down to these other kind of things that I've marked. Okay, so on Wednesday we did this thing called the first shifting theorem. All right, so the FST stands for first shifting theorem. So suppose we're transforming a product. Okay, so there's my product. Yep. So, and it's got an exponential as part of the product. What the FST says is that, okay, well, you can compute the transform, it's not that hard, but basically all you do is you compute the transform of little g to get big G of s, and then you shift it a units. Okay, let me say that again. To compute this product, you just concentrate on the function little g. Compute the transform of little g to get big G of s, and then you don't want big G of s, you want big G of s plus a. So that's why it's called a shifting theorem, because you take something and you shift it, right? So it's not just big G of s, it's big G of s plus some shift, plus a. Okay? So, before I go any further, questions? Questions? I think most students who have trouble with the first shifting theorem, they're either not sure where to start, or they don't realise that you want the function big G of s first, and then you shift it. Okay, so let's look at a special case in the table. I know I'm concentrating on the table a bit, but it's important. Okay, let's have a look. Let's have a look at this one here. You come back. All right, let's have a look at this orange one. Okay, is that a special case of the first shifting theorem? Ja oder nein? Ja, jawohl. Okay, so what is, in that orange box, I know it's a bit hard to see the colour, but the orange box, what is G of t, little g of t? T. Okay, so if we were given this thing, right? What we, and I mean, we already have the transform there, but if we were given this, we would forget about the exponential and we would look at the t function and compute the transform of t? What is the transform of t according to that table?
1 on s squared.
1 on s squared. So if we go up to the second row, we go, haha, that's exactly what I want. 1 on s squared. But look here, it's been shifted. Oh my God. It's been shifted a units. Okay? So, just got to manage the algebra. Replace s with s plus a, all in brackets. Okay, the number of times I've had to explain that because people's algebra is sometimes a bit rusty. So the best advice I can give, replace s with s plus a in brackets.
Is it the exponent that causes the shifting?
I think when you multiply, so what causes the shift? That's really what you're asking, right? Yeah. So I did a little proof in the lecture, but it was like 9 a.m, so people have probably forgotten. If you put an exponential in here, right? So e to the negative st times e to the negative at, you can factor out the t, and you get s plus a. That's where it comes from. So algebraically, it makes sense, right? It's a good question. Okay? Other questions? Okay. All right, so that was the first shift. You've got to say that very carefully, right? First shifting theorem. Today, we're going to look at the second shifting theorem, very creatively named, might I add. First shifting theorem comes first, the second shifting theorem comes second. There's no third shifting theorem though, so it's okay. But let's look at some of this other stuff first, okay? Let's actually just dissect the table because, you know, the table is your friend, really. The table is your good friend, and you should get to know the table, you know, definitely before the exam. You want to know what's on the table and what's not, you know. So let's dissect this a little bit more. Down the bottom are actually, in my opinion, the most important transforms, okay? This is actually why those bottom four, actually the bottom three, are actually why we can use these transform methods to solve problems, okay? And I think I said this on Wednesday, but again, people are sleepy. If I transform the derivative of something, right? The table says the derivative disappears. There's no big G dash there, right? So basically, if this is a solution from, say, a part of a differential equation, I can transform that and get rid of the derivative. Then I can solve for this big G of s and then transform everything back using the table. Same here. Now, you've got derivatives here, but they're just initial conditions, so they're easy. But let's play a little game. Let's look at this one. Okay, this is saying, I'll have a look at this in a minute. If you have t times a function and you transform it, it's the negative of the derivative of the transform. Let me say that again. It's the negative of the derivative of the transform. Okay, so let's actually look here and differentiate. All right, so I'm going to go up here and we're going to say, all right, g of s g. All right, so that's just a little g. All right, so now think back to week 1 of this course. So long ago. I want to differentiate that with respect to s. What method can I use? What method? What method rings a bell? Leibniz. Leibniz. Right, so let's bam, bam, right? So what do I do? Leibniz is the correct one way of doing it. How can I differentiate this integral? What do I do from a procedural or from a method perspective?
You move the derivative inside of the integral.
Exactly, exactly. That's a good start, right? And in this context, I'm paying attention to see whether I've got constants here. So think of 0 as a constant, think of infinity as a constant. It's not great, but we can do that. Okay, so we've got t's in there. Let's differentiate with respect to s. Negative t is going to come to the front, and that's it, right? So that negative t is going to come to the front. And I'm left with this. Okay, so I can pair this guy up with this guy, and I can bring the negative sign out the front. Okay, what is that? That is the negative of the Laplace transform of t times little g. Okay? So let's relate it back to what we have on our table down here. So to prove that, we've used Leibniz rule. Okay? So how good's that? We actually used Leibniz rule for something. It's kind of nice, right? Kind of nice. Questions? Would you be asked to do something like that in the exam? Maybe. Maybe. If you've got like a text box or an essay box, maybe. Maybe at least justify something, you know? Questions? Okay. All right, so let's move on to the second shifting theorem. But before that, let's remind ourselves about the first shifting theorem. I'll come back to you later, table, because like I said, these are the really important things. For differential equations, these are the most important transforms. Okay, but we're still just getting to know them a bit. All right, so let me just find my notes. Okay, so I know I've sort of jammed it in here. This is e to the t times t squared all over 2. So it's a product of e to the t with t squared all over 2. I wrote that down a little bit messily, so sorry about that. Okay, FST. From a strategy point of view, the most important thing is to compute the basic transform of little g of t and then shift it. Okay, if you can do that, it's fine. If you can do that, it's fine. Okay, so this is the most important sort of strategy advice. Camera tracking off. Okay. All right. So in this, part A is just the transform of e to the 2t times t cubed, and then part B is the inverse transform. So you've got to go both ways with these things, okay? And the table's helpful, right? So with part A, my value A would be negative 2. My function little g of t would be t cubed. So compute the transform of t cubed and then shift it. Okay, so let's have a look. Here I'm taking the Laplace transform of t cubed. I go to my table. Where are you? This will do. So I want the transform of t cubed. So m equals 3. Go over here, it'll be 3 factorial on s to the power 4. So that's where that comes in. And then I shift this function 2 units, okay? A units. 2 units to the right in this case. Okay? Questions? It's quite important, right? And I know we were joking about multiplication tables on Wednesday, right? But you really just got to know how to use the table. Okay, so what about going the other way? Well, here we start with this, so this is already shifted. So, you know, I'm trying to look for a function and a value of A that makes sense here, that puts it into a form like that. Okay, so it's a little bit of algebraic kind of discovery or recognition to get here. Okay, so if I look for it here, it's got s minus 1 all in brackets. So if I'm trying to make a function out of that in this style, I would say, okay, what about if a equals negative 1, and then big G of s will be 1 on s cubed? Okay, if I have those 2 bits, then I can use the first shifting theorem to untransform everything, okay? So if big G of s is 1 on s cubed, the inverse transform of that is this, 1 on a half t squared, okay? And then you just multiply by e to the a times t times that, okay? So that's 1. All right? Now I've sort of squashed it in there, but questions? Comments? Observations? Criticisms? Commentaries? So my advice, do as many of these problems as you can. Okay, do as many as you can. So let's see if we can continue. Do I have... Oh, yeah. Yeah, okay. Let's do these ones. Okay, I'll just zoom in a bit. How's everyone going at home? Any questions? How many people are watching at home? 18. 18 in full effect. All right. So like I said before, the method is super important. Okay? The method is super important. So let's have a look and see what we can do here. Just give me a minute. Yep, you'll do. All right, so let's look at the first one. You're asked to transform the product of e to the t times sine of t. So we're looking for a product involving an exponential. Okay, who can tell me the value of a and the function g of t here?
A is minus 1, g is sine t.
Yeah, perfecto. That's a pretty good starting point, I think. So to fit that with our function, we can say, okay, well, let's let a equal negative 1 and little g of t equals sine t. Now, we're interested in really we're interested in the transform of sine t. So let's go to our Okay, what's the transform of sine t going to be? Who can tell me? Who?
It would be 1 over 1 plus s squared.
Yeah. Exactly, right? So I go down the left-hand side of my column till I find a sine function. B would be 1 in this case. So I go, okay, here I am. I'll go over here and plug in b equals 1, so 1 all over s squared plus 1. Exactly what you said, right? So okay, so note how I'm using the language that says I'm clearly drawing on a table here. Why would you want to do that? Does anybody know? Why would I want to say from the table, or I'm using a table here?
Is it just kind of to show you're working out, just to make sure that you know what you're doing?
Yeah, so it's sort of convincing yourself that you're doing something, but also if you've got an essay box or a text box, you can point to the table. You don't have to prove everything, right? Okay, so now what? First shifting theorem. Okay, so it's the transform shifted a units, and in this case, a equals -1. So I'm going to take s, replace it with s minus 1 in brackets, and I'll get this. Okay. Oop. Sorry, let me just push that into screen. Okay, do I need to simplify that? Not really. It's probably better if you don't. Okay, you can clearly see the shift.
I was just curious because I think I may have forgotten, but if we're applying a multiple to the to our g function, do we just add the Laplace theorem of that multiple, of that coefficient?
Yeah. So it's a really good question. Because the Laplace transform involves an integral, it's a linear operator, right? So if you're adding 2, you can break them up. If you're multiplying by say the number 3, you can pull the number 3 out, right? So for example, let's say this was that bad boy there. Yeah? So I think what you're suggesting is you can just take the constant 3 and bring it out the front. Is that what you're saying?
Oh, no, I was adding, as in, did we need to add the Laplace transform of 3? Because I think I may have seen that in the question somewhere.
No. Oh, well, yeah. Well, let's say it's this. Okay, so it's 3 times the Laplace transform of e to the t sine t plus 4 times the Laplace transform of 1. So that's the linearity. It's a linear thing, so you can break it up, which is nice. Okay. All right, what about part B? Part B. Okay, so in part B, we want the inverse transform. So what we've got to find here is a function big G and a value of little a. All right, so what is my function big G of S? Big G of S, what is it? 1 over s squared, exactly. And what would a be? You're on a roll. 2, exactly. Okay. Okay, so let's use that down here by the first shifting theorem. Okay, so if I go back to my first shifting theorem, where are you? You're there. So we're over in this domain now, and we're going to go over here. So okay, so that's big G of S. We want little g. What is the inverse transform of little g? Let's have a look. Who can tell me what is the inverse transform of 1 on S squared? T, exactly, right? It's not a mystery. Okay, it's going to be T times E to the negative 2T, all right? If that sort of triggers you, you can write it like this. Okay. So they look easy when I do it, and maybe they are super easy, but sometimes you'll get functions and examples that don't quite fit the table, and you've got to get a bit more creative. Questions? Comments? Observations? Complaints? Anyone at home? Is anyone at home still awake? What have you got for me? So that is the first shifting theorem. Use it well, use it wisely. You'll definitely be tested on this at some point. I almost guarantee it. All right. So what else have we got? Aha, the second shifting theorem. As if one shifting theorem wasn't enough, we need more. The second shifting theorem. Okay, so let's have a look at it. The second shifting theorem involves the product of some shifted function and some step function. Okay, so this u function is a special function called the Heaviside step function. So before we get to this, let's play a little game with the Heaviside step function. Let me see if I can find it in my notes somewhere. Yes. All right. We're going to talk about the Heaviside step function for a second. Okay? So let's go back to our table. Here we are. Heaviside step function, Heaviside step function. Okay, so there's two bits here, and they're super important, both of them. Okay, so before we tackle something like this second shifting theorem, let's just acquaint ourselves with these switching functions a little bit, okay? So I'm going to set you all a little challenge. Heaviside step function. Okay. Does anybody recognise the name Heaviside? Anyone? Yeah? Here's an engineer from back in the day. Very good one. They named this function after him. So let's have a look at what it is. Okay, it's 0, so C is some positive function, right? A positive value. It's 0 to the left of C, it's 1 to the right of C, and it's halfway at t equals C. So if I draw a little picture, and let's say C's here, right? To the left of C, the function 0. To the right of C, it's 1. And at C, it's 1/2. Okay? So you can kind of think it like a switch and times the horizontal axis. At some point, a switch gets flicked, turned on, and your function instantly jumps up. Right? Has anyone seen functions like this before? Where have you seen them?
I think they mentioned this like in electrical, where like you have a step function where like as soon as there's no current going through or something like that, it's got 0 input and output, and then as soon as a current goes through it goes straight up.
Yeah. That's a pretty good description. So let me give you a little example here. Oh, hang on. Okay, here's the challenge on a Friday afternoon. I want you to sketch the graph of that function. Everyone at home, wake up. Right? What does this function look like? There's 2 switching points. Okay? There's 2 switching points. What does this function look like? What does it look like? If anybody can give me a graph of it, I would love to see it. What do you think, gentlemen? What would the graph of that function look like? Any idea? All right, so grab a pen, grab a pencil. Try to sketch out that function. It's not as easy as you think. Ooh. Okay, let's have a look. It's pretty good. Okay. Can I use it? All right. Here's the first entry. I think it's this one here, right? Yeah. So let me just add a few bits. I think here, okay. All right, let's see. So for t less than 1, what's that? 0, right? For t less than 1, that's also 0, because the switching hasn't happened yet for either of them. Right, so we're in this space here. This is off, that's also off. Okay, so we're on 0 here. We get to 1, this gets switched on. This is not switched on yet. So we go boop, and it's just 1. And we get to 2, t equals 2, this is still on, this gets switched on. So this will be 1 plus 3, bloop, up to 4. What about, what would the value of the function be at the points of jumpy, like? Is that what you're going to say? Hey, that's all right. It's a team effort. Okay, so if you look closely, the discontinuity points are right in the middle. They're kind of like the average of the jump, right? So now we're getting into some weird territory because the switching on, we can also switch things off, right? We can switch things off. So let me give you an example, right? That's excellent. They're harder to draw than you think, okay? They look easy when you draw them, but to actually do it takes a fair bit of effort. Let's do some switching off. So, you know, this was something like this, 1, 2. Okay, what about this one? So now I've got a negative sign in the mix. What would the graph of that function look like? Yeah, that is the heaviside function, exactly. Somebody's still alive at home, that's great. What would the graph of that look like? Anyone want to make a submission?
Just using my best knowledge of transformations. So you get like, I guess you start off with the ut minus 3, so that'd be pretty much the heavy-sided, but you shift it 3 to the right. So it's going to be like at the point 3, it will go up to the switch on. But then when we're going negative, you like flip it over. So if you go from the right to the left, it kind of looks like it's switching on. And then you shift all of that up 1 unit, and you get that graph, I think.
Okay, all right, yeah. That's a little complicated on a Friday afternoon, but you're just speaking and thinking at the same time, so that's fine. It's like a stream of consciousness sometimes, right? I have those. I have those days too. Who can boil that down a bit? Yes. Even just draw it with your fingers. Tell me what it looks like. Do some air drawing or something.
So, in a manner of speaking, you're basically reflecting it over both axes and then shifting it by 3.
Yeah. Yep. So I reckon I can even go simpler than both of those things. So you're both right. Okay. So for t less than 3, what's the value of this? It's 0. So what's the graph? 1. And for t greater than 3, what's this value? 1. So 1 minus 1, 0. Okay, so if I ever get confused with these, I just break it up. The left-hand part, the right-hand part, and then there's the jump point. Okay, so if I was drawing a picture like this, okay, something happens at 3. It's 1 up until then. This becomes 1 for t greater than 3. And it's half in the middle. So that's a really rough example of where you have something on and you switch it off. Okay? All right, are you ready for something spectacular? I hope everyone at home's tuning in. Okay, what does this look like? Oh yeah. Yeah. Oh no, gone a bit crazy now. What does this look like?
So the switch is turned on at 1, and then it turns off at 2, and then turns back on at 3.
Yes, that's it. See, this is the kind of thinking that is great, right? You can just see the switches. Brilliant. Yep. So if I was drawing this, it'd go off, on, off, right? Okay, see if you are with me. Okay, so something happens at 1, something happens at 2, and something happens at 3. All right, so this is off and then it gets turned on, but both of these are still off. Okay, this is on, this gets turned on, 1 minus 1 is 0, that's still off. This, both of these are still on and negated, this gets like this. Okay, let me check that. That's off. Yep. Yep. Okay. So it's getting a bit more difficult now, right? So this is the Heaviside step function. It looks innocent in isolation, but when you start putting things together, it gets crazy, right? Okay. So what about if we wanted to do the transform of this? What if we want to do the transform of this? Well, I'm glad you asked. Now you will, if you solve differential equations with discontinuous right-hand sides, Heaviside functions can come into it. So this is a transform that you may do a lot in this course. Okay, so we know that this is a linear thing. Let's go to our table and look up the transform for that, that, and that. See what we can come up with. All right, so it would be here, exponential all over S. So in our case, C is going to be 1, 2, and 3, and there's 3 cases. Okay. Okay. So this switching, like sometimes it gives you nightmares, right? Because you're not sure whether something's switched on or switched off. And there's so many things that are interacting, you're like, oh my God, I can't handle this. But you can do it. And if you get worried, you can just say, oh, okay, this is what happens before the switch, this is what happens after the switch. Questions? Questions? We haven't got to the second shifting theorem yet, but we will, don't worry.
My question is, what applications does Heaviside step function have?
Yeah, so think of a, yeah, okay. So think of a vibrating spring mass system, right? So you've got a spring, you've got a mass, and it's attached, say, to the ceiling, right? And it's just sitting there, right? And I tap it, right? Or I put some constant force into it. I switch something on that affects the system, okay? That's where the Heaviside function comes in, right? So you can think of this as, nothing's happening, then something happens for a little while, then it gets switched off, right? And then nothing happens and it gets switched on, and it stays on. Okay, so these sort of, you can think of them as pulses maybe as well. They're just on for a minute and then off, on, off, on, off. Okay, but you can do all sorts of weird and wacky things with Heaviside step functions. So we'll see them in differential equations. So, I think this is the slide I keep going back to because lots of people want to know, right? So you've got something like this. This could be a spring mass system, right? When you're modeling it. And you've got this switching function as the external driving force. Does that answer your question? Yeah. So remember, we're not doing transforms just for fun. We're going to do something with them. We're going to solve some problems, but we need to know how they work first. Okay? Other questions? All right, let's take a 10-minute break, and we'll be back. And I'm going to do some revision in the next lecture. Okay, so stay tuned, everybody. All right. So today I thought we could talk about revision for lab test 2. Okay, so remember, lab test 2, there's 3 broad topics. The first topic is double integrals, double integration. The second topic is differential equations. And the third topic, matrices, right? So I thought this was a good question, and it might be in Mobius this week, I'm not sure, because I didn't cover one of these in lectures. So I thought, I'm going to do this in the revision Friday afternoon lecture. Okay, so let's have a look at it. This is a 2-part question. So you've got a symmetric matrix. So whenever you see a symmetric matrix, you go, yes, yes, this is easy, right? Because symmetric matrices have eigenvalues that are always real. There's no repetition, they're always distinct. And to compute the inverse, or the matrix that diagonalizes this, you get the eigenvectors and you normalize them. And then the inverse of that matrix is its transpose. So symmetric matrices are nice, and they're the entry level. They're like the starter pack for this sort of study. Okay, all right, so let's read a bit further. The symmetric matrix here has 3 distinct eigenvalues. Of course it would, because it's symmetric, right? 2 of the 3 eigenvalues are 14 and negative 14. Suppose that the third eigenvalue is k. What is the value of k? Now, the tempting thing would be to go and actually work out what k is, but there's a smarter way to do it.
Well, since it's a symmetric matrix, you can take the trace of it, and that would be equal to all the eigenvalues, like the sum of all the eigenvalues.
Yep, exactly. So I haven't mentioned this in lectures. You would have seen it in 1231, Math 1231, I think. But let's have a look at a thing called the trace. Okay, so you look down the main diagonal and you add those values together. Okay, so let's call this A. So the trace of A is 10 plus 22 plus negative 4. Okay? So, what does that give you? Yeah. Did I get that right? Yep. So 28. Okay. Now, like you were saying, the sum of that main diagonal is equal to the sum of the matrices eigenvalues. Okay? So let me write that down. That's a theorem, right? The sum of the eigenvalues. Okay, so we told 2 of the eigenvalues. Let's say that's lambda 2 and lambda 3, right? All right, so the sum of the main diagonal, the trace, is 28. The sum of our 3 eigenvalues has got to be whatever the missing eigenvalue is. So we can conclude that that missing eigenvalue is 28. Okay, so this is a general theorem. You might say, why does it work? Well, if you diagonalize a matrix like this one, and you look down the main diagonal, you're going to have the eigenvalues, right? the trace, like to compute the trace, it's not affected by those operations, so multiplication, those sorts of things, okay? So if I was given a question like this and you don't know, this is great, so 28. Now, of course, if you don't want to learn that or you forget it, you can still go through and calculate all the eigenvalues. Right, it'd be a pain in the butt though, right? I mean, nobody's got time for that, really. Who would want to do that? You do that as a last resort.
Does this rule apply only for symmetric matrices?
No, I don't think so. I think it's a general thing, right? I think it's a general thing. But as I've said, symmetric matrices are very nice, okay? So anything that's diagonalizable, this should work, okay? All right, so that's the first part of the question. You were given that the symmetric matrix A has 3 linearly independent eigenvectors, that, and that, with corresponding, so we're getting that, and this will be 28, right? Okay. So this would be the eigenvector, so this is like your V1, corresponding to lambda 1. Oh, actually, I'll just, okay, so let me do that. Yep, okay, that's okay. All right, so I'm just going to change those subscripts to make them a bit more usable down here. All right, so this would be for that one, this would be for that one, and this would be for that one. Okay? All right, so what they're asking you to do here is find an orthogonal matrix Q such that it diagonalizes A. Okay? So who can tell me how would we actually do this? How would we do this? What's the strat? What is the strategy? Yeah, you've been good.
So I guess the first thing to recognize is that like we're using a transpose as opposed to the one we're like probably used to seeing, which is the inverse. So I think you said earlier, like the property of a orthogonalized matrix is that your transpose and your inverse is the same, something like that. So your Q, your normal Q, would be just pretty much your the eigenvectors in order as columns. So you'll get a 3 by 3, whereas like the first column is 6, 3, minus 2, 3, minus 2, 6, and then 2, minus 6, minus 3. And then you orthogonalize it by getting the magnitude of each of those column vectors and dividing it by the magnitude to get the orthonormal? Is that
Yeah. Perfect. So basically, if you're doing Math 1A right now, you'd be saying, hey, I'm going to take those things and write them as a matrix in order. But with this orthogonal thing, like you say, you just want to divide by the length of each of the vectors, right? You want to normalize the columns. Orthonormal, right? The columns have length 1 and they're linearly independent, right? So who can tell me what are the lengths of each of those vectors, v1, v2, v3? It's all the same value. Isn't that handy? That you only got to compute one thing. What is it? Yep. So the length will be 7, and then you divide by the length. Okay? So if we look here, let's say I wanted to find the length of this vector, 6 squared plus 3 squared plus 2 squared. Okay? 49. So Q is going to be okay, that's a general thing. And so it'll be something like this. right? You have, so here, yeah? So basically you divide each of these terms by 7 and put them into this box. Making sure you don't make a mistake. Because when I'm doing it, I make a mistake all the time. I mean, wouldn't it be great if you could just put the 1/7 out the front of the matrix? I don't know if you can do that with the Mobius interface, but it would be good to try. Can someone try that and report back? Oh, you can? Yes. So 1/7 multiplied matrix. Excellent. That's a much better way to do it, right? Questions? So remember, symmetric matrices are special. Symmetric matrices are special. So when you've got that line of symmetry down the main diagonal, you should be going, yes, this is super easy. Okay? Yep.
Yeah, I have a two-pronged question. So for these types of matrices, do they always have, do the eigenvectors always have to have a magnitude of 1? Oh, and
Orthonormal. So
oh yeah, so they all have to have the same.
you see, well, yeah. So orthogonal, and to make it orthonormal, you give the you give the columns length 1. Yeah, yeah. But normally when you're diagonalizing, you got some matrix. Who cares if it's symmetric or not? You don't need to do this. You don't need to normalize everything, right? You can do it. You're not going to be wrong. Yeah, it's not. You're not going to be wrong if you have another thing and you normalize the columns. It's still correct. Yeah. Other questions? Enjoy the weekend. Okay. So that's a good question. Questions at home. What's happening at home, everybody? Not a lot. Okay. My wife was on the national news today. Very proud moment. Talking about dementia research. Angela Bishop is interviewing her. I'm watching before the lecture. I'm like, oh, it's so good. I was nervous for her. No. I rang her afterwards. Okay, let's do some lab test 2. All right, so I'll go here. This is what we were doing the other day. All right, so I'll go here. Shut up. This is what we were doing the other day. Gosh, I sound so gay. All right. All right, so we did quite a few of these. And we had our little shields. And where did we get up to? Oh yeah, we got up to there. All right. Oops. Okay, all right, so let's do some double integrals. Now with double integrals, one of the key things is to draw a picture whenever you can, okay? Like most people have problems if they don't draw a diagram. Now, like I said, you can do these problems by integration by parts, but the way they've set up the questions, they don't want you doing that, okay? I mean, it's my little method, I love it, but they want you to do something else, okay? So, what's going on with this integral? Why is this integral difficult or potentially difficult? Why is it a pain in the butt? Anybody know?
It's probably hard to integrate straight up.
It is. Getting the wallet out again. Okay. Okay. If anyone can come up with the antiderivative of this with respect to y, here's the cash. There's the cash. Okay. Can you come up with an antiderivative of that in terms of simple elementary functions? I'll tell you what, I'll up the ante. Gosh, I've got money today. Holy moly. Oh, I know the bands. I'm flashing the bands, as someone said. Right, I had to go home and look that up. Right, I'm not going to lie. So this is annoying because you can't integrate it the way it's set up. Because you do the inside integral first with respect to y, you can't do it. Okay, so what's the strategy that we have for dealing with a problem like this? What's the overall strategy? What's it called? Yeah, reverse the order, right? Reverse the order of integration. Okay, so it starts with a picture. Let's draw something and we can have a look. Okay, so we've got this. Nine cos 3x, 3y, sorry. And usually what we would do that inside integral first, and then we would move on to the outside integral. But this one's difficult because you can't do the inside integral first in terms of simple things. Oh, hang on, I've not put those integrals in, so there should be an x in here. X. So that's important, right? That dramatically changes the problem. Okay, so that's an x. Okay, so let's draw a picture of the region of integration. So we're in the xy plane. Y is between x and 1. And x is between 0 and 1. Okay. As a shape, what is that region going to look like? As a general shape, what's it going to be? Triangle, right? Or a wedge, something like that. Yeah, exactly. So let's draw it and we can re-describe it then. So the way I like to draw it, I draw all the boundary parts first. Yeah? So draw the line x equals 0, that's the y-axis, of course. Draw the line x equals 1. X equals 1. Draw the line y equals 1. Draw the line y equals x. Okay. So you said that it was a triangular region. There's two triangles there. I'm confused. Which one is it? Is it the top one or the bottom one? The left one or the right one? The top. Yeah. Are you guessing or you?
Yeah, I guess. No, I read that it was above x but below 1 for the y.
Exactly. So remember, well, y goes vertically, right? And so y is above x. There's the line x. So it's right? And x is between 0 and 1. So it goes like that. So it's definitely that bit there. All right. So thank you. Let's re-describe it now. So it's not in the perfect way, but let's re-describe it. Okay. So instead of having y equals x, let's flip the script. X equals y. Oh my God. And instead of having two parallel x lines, let's have two parallel y lines. Okay, so if I was re-describing this, I would use those two lines, right? And then go this way. Okay? So if I'm redescribing this, they're my two parallel lines, so y is between 0 and 1. And what's x going to be between? Hang on. Yeah, what's x going to be between? Would it be between 0 and y? 0 and y, exactly. Because x is horizontal, right? OMG. All right. So now we're in a position to set up our integral. Change the order of integration with this setup, and then we can evaluate it. Okay, so is this the easiest integration you've ever done? What is the integral of 9 cos 3y over y with respect to x? You just multiply by x, right? How good's that? Okay, when I plug in y for x and 0 for x, I'm going to get some nice cancellation. Okay, we can handle that. We can handle that integral. It's going to integrate to something like 3 sine 3y. Okay, so when we plug in y equals 0, we'll get 0. That's it. Okay, 3 sine 3. Now you can integrate that by parts if you want to. I don't think that's what they want you to do. You can fight the power if you want to, but you still need to know this method, I guess. Questions? Okay. All right, let's do another one. Let's do a polar problem. Let's do a polar problem. Let's see if I've got one of those. Aha. Okay, for everyone at home. All right. So remember, when we've got curved regions, polar coordinates are a good option. Potentially. Potentially. Enjoy it.
I've got an exam.
Oh, no worries. What's it for?
Materials.
Go. Do it. 100%. I believe in you. On a Friday afternoon, you've got an exam. Gosh. Okay. So who can tell me, how would you describe the yellow region? Anyone else who's got an exam, feel free to go. How would you describe the yellow region in terms of polars? So theta's between what? Yep, theta's between 0 and pi on 2, so it's a quarter of a revolution. And what about the r? Yeah, between 1 and 2. Perfecto. So if I was doing this question, I know what my region's going to be. And let's have a look at the function that we're integrating, the integrand. There it is there. So I'm going to replace x with r cos theta. Hang on, I'm going to replace y with r sine theta. And what do I replace the area element dA with? RD theta. Okay? RD theta. So if you can remember that, happy days. Okay? So, here's one that I've done earlier. Okay, you can see here, I've just scratched it out. X equals r cos theta, y equals r, don't write like this, be better than me. Y equals r sine theta, dA equals r dr d theta. 15x squared y is 15r squared cos squared r sine theta. And I know in this setup, my region something like that. Okay, sometimes describing the region is the most difficult part. Yeah? Okay. So that's going to become that, and remember dA is r dr d theta. Yep. So let's have a look at the question carefully. There's too much English in these questions. You know, would you agree? There's too much English. Nobody's got time to read all that stuff. Right? Does anybody read it? People just go straight to the text box? Like seriously, like it's maths, it's not English, right? First, write the expression in polar coordinates as a function of r and theta. Okay? So here, this would be something like that. So 15 r cubed cos squared. You just got to watch the syntax. Yeah. And then now this is a bit of a tricky one, right? They're trying to trick you there in part 2. Next, given that in polar coordinates the area element is a function of r and theta, right? Well, I'm not really, oh yeah, dr d theta. Write down the function in maple syntax below. What would the function be? R. Now, when I was inputting that, I wasn't sure whether to put the multiplication sign. Right? I didn't, and it was right. So I think that's the way they want you to enter it. Okay, and the last part, hence evaluate the integral. So that's it. Okay. So you're integrating from 0 to pi on 2 and from 1 to 2 of that mess. And the thing that it's actually nice about it is that it is a polar rectangle, which means you can split up the double integral as a product. So you can do this integral times that integral. Right? Just, you can see I've made a few mistakes there. But basically you're integrating sine of cos squared and you're integrating r to the power 4. Okay? So you can see I made many, many mistakes. Okay, if you don't want to split it up into the product of two intervals, you don't have to. So forget that. You know when you just keep putting stuff into maple and it doesn't work? Okay. So for this integral, it's basically you can use the chain rule or substitution, or you can just write down the answer. You know that it's going to be a cos cubed. Okay? Questions? Let's go back, test our answer. Should we do how did I do? Let's hope it's right this time. ChatGPT doesn't have to save me again. Yeah, it's all right. Okay. Questions? Okay. Questions at home? Yeah. Good job. Thank you, Jonathan. And Rishuan, thank you. Okay. Let's have a look at another one. Okay, all right. This one's a little harder, I think, anyway. Have you seen this? Do you know of this? Is it familiar? You've got a circle within a circle. So 2 circles. And you've got sort of a sector or a wedge of the small circle, and it's in yellow. That's the region of integration. Okay? That is the region of integration. Okay, so let's put our polar hats on, right? What are what is a correct description of the yellow region in polar coordinates? In polar coordinates, yes.
R is from 0 to cos theta, and then theta is from 0 to 1/6 pi.
Not quite, just say it again. So let's do the R one first. So R is between
0 and cos theta.
correct. And theta?
Is from 0 to pi/6.
Pi/6. Yes, exactly. Excellent. So you can kind of see the question almost tells you that already. I mean, you can see it. I know that. But the question sort of already tells you that. It's like, hello, and it goes all the way to 0, right? R equals 0. So that's the only bound you need to come up with is the lower bound on R, and it goes right to R equals 0. So that seems like a logical thing to try. Yeah? Okay. All right, so let's have a look at the questions. Write down the function in polar coordinates, okay? So we use x equals r cos theta, y equals r sine theta, and you plug it in, and you can use, sine squared plus cos squared equals 1. Okay? So let me see if my writing's any better for that one. Oh yeah, it is, okay. So let me go back here. Okay, so for part 1, I've just put in x equals r cos theta, y equals r sine theta, and I get some simplification. Okay? So that's what I'm going to get. Yeah? All right, and let's go back to the description of the region. That's really the only thing you have to come up with. Okay? Because R, you can't go outside that curve, and it has to be greater than or equal to 0 to get anywhere. So that seems reasonable to me. Okay? All right, last question asks you to compute the integral. So here's my working. Okay, part 3. So note that this isn't a polar rectangle, by the way. So it's not as simple as the previous one I showed you. So you sort of have to do the inside and then the outside integral, which sucks, but you can do it. Okay? And the answer's in a bit of a weird form, but it works. Okay? Questions? I couldn't remember what the cos of pi on 6 was, so I just drew a little triangle, right? You can do that. You're going to have paper and pens with you. Questions? Okay? All right. Questions at home? Anything happening? How many have we still got hanging on? How many? Oh, lucky 13. Not connected. Oh, come back. Okay. So let's try it. How did I do? Oh, it's all green. Thank goodness. Okay. Aha, all right. So this is a slightly more difficult problem than you see in first year, okay? It is a variation of parameters problem, right? And the thing that makes it a little bit annoying is this right-hand side, okay? Maybe you can solve this using first-year techniques. You probably, I reckon you could, but you'd have to be very careful with your homogeneous choice, right? Or your particular solution choice, sorry. Okay? So they're already telling you some nice stuff. They're telling you y1 solves the homogeneous problem. y2 solves the homogeneous problem. Okay? And then you're given the formula for the particular solution in terms of y1 and y2. Okay? So there's a couple of things they're asking. Gosh, you're even given the Wronskian. What do you even have to do here? Just press how did I do once and you'll get the mark. Right? What do they actually want you to do? Compute I1. Oh, there it is. Okay? So basically you take that, you put it in there. You take that, you put it in there. You take that, you put it in there. And you take that, and you put it in there. And you do an integration. Okay? And the same for I2. Yeah? It's pretty easy, I think, as long and you check your answers. But you don't check your answers too early because there's another one down the bottom. What does W of x represent? Now, more English. Oh my God. Too much English. Okay. It's not very comfy. All right. What does W of x represent? Another solution to the homogeneous equation associated to the non-homogeneous. What the hell does that even mean? Who wrote this? Was English their third or fourth language? I don't know. Okay, does that sound correct to anyone? Does that even make sense? Another solution to the homogeneous equation associated to the non-homogeneous one. That doesn't make sense. Right? Like that's just garbage. That's something you would get from ChatGPT. Right? We should ask ChatGPT to talk about this. Or what's Musk's one? The AI? Grok. Yeah, we should ask that. Yeah. I'm hearing this. Okay, let's look at the second part. The Jacobian determinant of the transformation from the homogeneous to the non-homogeneous solutions. What does that mean? That doesn't make sense either. This is just pure AI. Right? That's what we should get AI to come up with the distractors. Okay, what about the third one, but the third bowl of porridge, was that just right? Maybe. The Wronskian determinant of the fundamental solutions. Does that sound right? It's got a W, Wronskian, W of x. Okay, if I was betting the cash in my wallet, I would bet for number 3. Okay, but okay, I have a question, right? If English is your second or third or fourth language, how are you meant to understand something like that? Like seriously, do you just look at it and go, I can't understand it, I'll just move to something else? Please tell me, because I'm curious. Right? Even an English speaker would not really be able to understand that. I'll give you $20 if you can explain that, what that means to me right now. Oh, the hands go up.
Is it saying that it could be a solution to YH and YP? That, I mean...
Is that possible?
I don't
think it is.
No.
But maybe that's what they're trying to. Maybe that's what they're trying to do. Another solution to the homogeneous equation associated to the non-homogeneous. Another solution. So a third solution?
Yeah, as an alternative.
No. Maybe I'm starting to understand. Okay. That is what whoever wrote that needs to confess. Okay. What do people think at home? Is that just unhinged? Nothing is happening. It's all happening here, I reckon, on a Friday afternoon. Okay. Click to get back in sync. Okay. Oh, hello. Are we still out of sync? All right. Okay, same sort of problem. Same. Or I1 plus I2. Okay, all right, let's deconstruct this. Put in our best language skills. Okay. Sorry, I can't make it too big. All right. You've got some problem up the top and you're told I1 is this, I2 is that. Okay, let's go to question number 3. What does I1 plus I2 represent? Okay, I've clicked one of them, but I don't know if it's right or not. Okay, what does I1 plus I2 represent? Okay, let's take a vote. Who thinks it's number 1? Come on. I've ticked number 1. Does that sway you at all? Okay, who thinks it's number 2? The space of all solutions to the non-homogeneous equations. Number 3? A particular solution to the non-homogeneous equation. I think it's number 3. I think it's number 3. Shall we? Yes. No, when you add them together. Yeah. So, and because it's not homogeneous, you can't just add the two things and get what you want, right, as a solution. Shall we try it? Shall we try? Shall we use our one like bullet in the chamber? Let's see. Oh, hang on. But if I'm wrong and I choose that one, hang on, I'll do that one. Oh, feels so good. Okay, wouldn't it be great if there was only 2 options? So if you did, how did I do? You know, it's the other one. Oh, they're too clever. All right, let's wrap things up. So we'll do more revision next week. I will get on to the second shifting theorem next week, I promise, on Tuesday. And yeah, come on down, have a chat. Have a good weekend. I'll see you next week. Hope everyone at home has a good weekend too.